record the video. Yeah, sure, why not? All right, we will read it first and then go through the solution. Okay, rope bridge. This rope bridge creaks as you walk along it. You aren't sure how old it is or whether it can even support your weight. It seems to support the elves just fine, though. The bridge spans a gorge which was carved out by the massive river far below you. You step carefully. As you do, the ropes stretch and twist. You decide to distract yourself by modeling rope physics. As you do. Maybe you can even figure out where not to step. Consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled toward the head. Due to nebulous reasoning involving Planck lengths, which are like the smallest length that physicists say even make any sense to talk about. It's look it up. It's very small. You should be able to model the positions of the knots on a two-dimensional grid. Then, by following a hypothetical series of motions, which is our puzzle input for the head, you can determine how the tail will move. Due to the aforementioned Planck lengths, the rope must be quite short. In fact, the head and tail must always be touching. Diagonally adjacent or even overlapping both count as touching. And we have some examples here that are all examples of them touching. All right. If the head is ever 2 steps directly up, down, left, or right from the tail must also move in that direction. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. So that's what we're doing here. You just need to work out where the tail goes as the head follows a position. No. You just need to work out where the tail goes as the head follows a series of motions. Assume the head and the tail both start at the same position, overlapping. For example, and there's a series of moves here that I, as always, copy it into my sample here. I didn't do this today, though. You know, apparently I'm getting like all antsy. I want to, and then I skip over the steps that help me move fast. It's dumb. Anyway, this series of motions move the head right 4 steps, then up 4 steps, then left 3 steps, then down 1 step, and so on. After each step, you'll need to update the position of the tail if the step means the head is no longer adjacent to the tail. Visually, these motions occur as follows. And yeah, S marks the starting position. Took me a second to spot that. So they all start in a corner, and then the head moves. They're still touching, so the tail doesn't move. Then the head moves again, and the tail follows it, etc., etc. Blah, 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 blah. Yeah, it's not very interesting. It's long-winded, though. After simulating the rope, you can count up all the positions the tail visited at least once. Sets. In this diagram, S again marks the starting position, which the tail also visited, and the pound sign marks other positions the tail visited. And you can see there's a nice little 3 here. So there are 13 positions the tail visited at least once. Simulate your complete hypothetical series of motions. How many positions does the tail of the rope visit at least once? And oh my god, did I have many good guesses until I reached this one? Because apparently there was a lot of ways to get this wrong that still gave 13. So I was like, okay, I'm done. Got my 13. So here we are. Yeah. Okay, so let's take a look. Yeah, the sample's tiny. The real input is enormous. And, it goes... It's not a preset coordinate system. You don't know how big it's going to get. So however you want to structure that doesn't really matter. I figured it made most sense to start at 0. So I defined, I knew we were going to count, which positions the tail had visited. And as usual, that's a set. Head X and head Y and tail X and tail Y, I'll set them all to 0. Then I create this function that, again, just like every other day where we have like a series of things that need to happen. I like to have a function that makes all the changes to the state and then I call that in a loop. So I can split those two tasks, split them up and deal with them separately. So the move part is, okay, this make it a little more readable like that. So these are the 4 directions, U, D, R, and L, up, down, right, and left. And if you want to go up, that means that your delta X and delta Y are going to be 0 and 1, 0 and -1, 1 and 0, -1 and 0. And then I use the move direction, which, from the file, that's what they are, R, U, L, and D. Use that as the key into this dictionary, and that means that I get my dx and dy out like that. And then I can add those to the head x and head y and get the new values for that. Okay, so next up is looking at the rules of motion for the tail here, where if it was ever 2 above or 2 below or 2 to the right or left, then move 1 in that direction as well. And that's what we're doing here. If the I can simplify this even more. Anyway, so yeah, if the difference between h, x, and tx is 2 and the other ones are equal, that means, okay, that's what we want to do. And then we take the difference between them and do an integer division by 2. Without the double slash, it would be, I would get a fraction or a float. So 2.0, and then all of a sudden my coordinate system is fractional, and that's, I do not have time for that. So I do that, and this is the same thing, only with the y coordinate being two different. Then we do this, and then finally I had a couple of false starts. You can, if you want, you can see the whole thing. But what we have here is basically if the distance between them is more than 1 in any direction, that means that they're not touching anymore. That's the criterion. So yeah, if we look at really anywhere, like this one, like if you go, all of these ones that are around it will always be, I don't know, you guys know how circles work. Why, I don't know why I'm being so, anyway. So yeah, if the difference between either the y or x coordinates is more than 1, then we have to make an adjustment. And I was kind of happy with this little trick here, because it took me longer than it should in my head. So this one, if the head is greater than the tail, then this is positive, and this is always going to be positive because we do the absolute, the absolute value of it. So that means that this will always be either a +1, -1, or 0, based on, with the difference here. It never complained about that. Oh, right, because it, yeah, anyway. And then I return the head x and the tail x, the head and tail positions. Okay, so we go through the lines, find the direction and the length, and then for, range, length, we perform the move, so we pass in the head and the tail and the direction, and we get the new head, tail out, and we add to the visited, and we are good to go. We get our 13 out, and my real answer was 6642. Yeah, I can barely remember all the corner cases that I got wrong that weren't covered in the example. There were a bunch of them. But, once I slowed down and actually read what it said in the description, it was, relatively straightforward. So that's what I did. Boom. And part B was, fun. Check this out. So part 2. Sorry. A rope snaps. Suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping toward you as you fall through the air. The ropes are moving too quickly to grab. You only have a few seconds to choose how to arch your body to avoid being hit. Fortunately, your simulation can be extended to support longer ropes. Yes, it can. Rather than 2 knots, you now must simulate a rope consisting of 10 knots. 1 knot is still the head and of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front of it, using the same rules as before. Using the same series of motions as the above example, but with the knots marked H 1, 2, 3, up to 9, the motions now occur as follows. And then we see like this whole long thing getting dragged around, and yeah, because the grid is so small, it never even moves. So then he comes up with a larger example. I didn't try that out. Doesn't matter, because this part was actually pretty easy. It's still the tail of the rope that we care about. And so really part B ended up being a generalization of part A, right? So part A is was the special the have I been over here all the time? Stupid camera. There we go. See, now it follows me, right? Yeah, there we go. Yeah, I just came from a Christmas party, so it's taking me a minute. Lost my train of thought. Yeah. Okay, so part B. It's a generalization of part A, right? Because part A is just like a knot with, that happens to have, it's a rope that happens to have 2 knots on it. And now we have to support, specifically 10, but it's as soon as we realize that, it's 10, then we might as well just make it variable, right? So that's what N is right here. And so instead of starting out saying there's a head and there's tail, we just say there's knots, and there is N of them. So this is a nice Python way of creating an array of a bunch of the same elements. So that turns into an array of 10 instances of 0.0 tuple. Then I split the, realizing this, that I split up the move function from part A into a move and a track. So move is for the head, because we follow the instructions, and track is for like each subsequent, knot on the daisy chain. We perform the tracking. So again, I think that's really helpful. You're having these functional bits where you don't have any state. It's just the thing that modifies the state makes it a lot easier to reason about. I think. So yeah, I changed the track to still it still has like head and tail terminology ish, because we're only looking at one at a time anyway, and it was faster to copy it that way. But it's fine. It's the same algorithm. We want to track it, and so it's fine. And then we just do the exact same thing again. We start out with we perform the move, and then for each knot on the rope, we track the one that's right ahead of us, and this is the one that's right ahead of us, and this is the one that's following, and then that gets updated, and that's it. And then we add the position of the final knot to the visited and return the length of it, and boom, that's it. That was real fun. And then that's when I realized, after doing that, we can probably turn part A into just part b n, no, file name, and then n equals 2. Then we don't need all this nonsense. Da 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 da. Boom. All right. Yeah. There we go. That was fun. A little fiddly, you know, and you know, I was really yeah, usually it's, you know, when you do the examples and they cover all the corner cases, but apparently I have more corner cases in my head than the author did this time. Or maybe they're just, you know, leaving more up to yeah, maybe it's intentional. I mean, that's fine too, I guess. It does kind of take the magic out of creating my unit tests first. Because that's usually, oh, yep, test pass, and then we can go. But not today. Anyway, this was fun. If you have any questions or comments, leave them below. Otherwise, like and subscribe, and I will see you tomorrow. Bye.